Welcome everyone to today's video. For this video, we're going to talk about single replacement chemical reactions and how to predict the products for them. A single replacement chemical reaction is just a reaction between a compound and an element. That is, there is a molecule or a compound that has two elements or ions that make that compound up, and that is doing a reaction with something that only has one element in it, or at least one type of element. The format typically follows this. It might look a little bit different depending on what compound and element we're working with, but AX representing the compound where element A is bonded with element X, A being something maybe you say has a positive charge when it undergoes a chemical reaction, X having a negative charge, B having, in this case, a positive charge or a negative charge depending on what element we're working with. One of these elements here is going to leave each other to bond with this element here when it undergoes that chemical reaction. In this case, A would be left alone, element A, whatever that is, and X would leave A in order to bond with B as a part of this chemical reaction. Let's go ahead and take a look at a few examples. Okay, one example of a single replacement chemical reaction is the reaction of iron 3 oxide. I just labeled that there so that everyone knows that, and aluminum. This is actually what makes thermite go. Thermite being that mixture of powders that when you ignite it, it burns extremely hot. They use it in certain welding types of situations, and it makes a pretty cool chemical reaction. But here's the first step that you need to follow when we go about trying to predict the products of this type of chemical reaction. First, we write down the elements and their individual charges down below. So in this here, we have iron and oxygen. This is iron 3, so we're just going to write Fe plus 3. All metals, and they're going to have a positive charge. This 3 just tells us that's what it's going to be. Oxygen is in group 6. That means it's going to have 6 electrons in its outer shell, so this is going to have a charge of -2. So does most other elements in that group, like sulfur. Aluminum is in group 3, right underneath boron, so it's going to have a +3 charge. Now, to figure out which is going to bond where, think of these elements like magnets. If we were to stick the elements together based on their charges, if they have like charges, they're going to want to repel, such as positives and positives or negatives and negatives. But opposite charges are going to want to attract to each other just like a magnet would. So we would find between these two, which would bond with aluminum. Iron has the same type of charge, a positive charge, so that's not going to want to bond with aluminum. Oxygen, though, has an opposite charge, so that's going to want to bond over here. So when we rewrite this, we write the positive charge first, and then the oxygen that bonds with it. And then iron, we write over here. Now, if you're trying to decide whether or not to write that by itself or include the 2, remember Hofbrinkel. If this element falls under this acronym, then you put a 2 after it. If not, you just leave it as is. And Fe does not appear on this. We're going to leave it as is. Now, aluminum has a +3 charge. Oxygen has a -2 charge. You just follow the same rules for writing chemical formulas for different compounds. I will post a video up here in the corner for you guys to watch if you are unfamiliar with those rules. But just go back and forth. What do we need more of? We need more oxygen here to even this out, so we'll add another 2. That makes more aluminum there, and then we just need 1 more oxygen there. So we have 1, 2, 3. That makes 6 here. We have 2. That makes 6 there. So that's going to be 2 aluminum, 2, 3 oxygen. And then that's it. Remember, keep in mind that we're not balancing chemical equations for this example. We're just predicting products for this, so we will do balancing equations next if we were to continue that. Let's go ahead and take a look at, we're going to look at 2 more examples. Okay, our second example we'll take a look at is sodium in water, H2O. I'll explain why I wrote H2O like this in a moment. This is a really fun chemical reaction too. I should start posting videos of these chemical reactions as we go on, because it's really kind of cool. Sodium is a very reactive metal. You'll never find it out in nature as pure sodium, because the moment water or oxygen touches it, it wants to undergo a chemical reaction and bond with something. Because of that, when you have a pure amount of it, it reacts pretty violently, and it's a pretty cool reaction. I'll post a video of it sometime. But we just follow the same rules here. We take a look at sodium. We rewrite the symbol down here with its charge. It's in group 1, so we just write Na+1. Sometimes I might write pluses that just, if you just see a plus and no number after it, that just means that it's +1. And then here's why I wrote water like this. I write it like this to show that when water undergoes a chemical reaction, one of the hydrogen leaves and the hydroxide becomes its own ion. So a hydrogen will split off from water and you'll be left up with a hydrogen ion and a hydroxide ion. So we would rewrite that as H, that is a +1 charge. And then we rewrite the hydroxide, OH, which has a -1 charge. Now we follow the same thing as last time. Sodium is by itself. It's going to want to bond with either this hydrogen or this hydroxide. We take a look. If the charges are the same, they're not going to want to bond with each other. If they are opposite, though, in charge, so positives and negatives, they're going to want to bond with each other. Hydrogen has the same charge, so we're not going to go with that one. Hydroxide, that has a negative. Sodium has a positive. These guys are going to want to bond with each other. So we'll rewrite that over here. NaOH. And then hydrogen is left by itself, so we'll just go plus H over here. Since this item's by itself, we're just going to take a look at Hofbrinkel to see if it falls under that list, and it does. It's the first one right there. So we'll put a 2 after it. If it wasn't in this list, we would just leave it as it was. This stuff is basically drain cleaner. Kind of nasty stuff. Be careful if you're working with it. That's hydrogen gas. Think Hindenburg. Very, very combustible. Okay, let's do one more example. Okay, last example for this video. This is something I do very common for demonstrations to make like hydrogen balloons and whatnot, and it's kind of fun. Zinc's a relatively cheap metal. Zinc, first step, we got to write the charges down. So zinc 2. I think zinc typically always has a +2 charge, but I always put that just to make sure everyone knows that. Zn +2. It's always positive. Metal is always positive. Oh, we'll get rid of that plus sign. HCl, that's hydrochloric acid. So this is an acid. This is if you were to like take this metal and take in a beaker filled with this stuff here. These are going to split off hydrogen from chlorine. So we'll write an H. That charge is, I'm going to rewrite that just a little bit bigger for you guys. H +1. It's in group 1. Chlorine is in the halogens, so that's chlorine -1, because it's 1 away from being a noble gas, having that full octet. And then we just find the opposite charges. Zinc is positive, so it's going to want to bond with the negative of over here. So we would rewrite that. Zn, positive gets written first. Cl. And then hydrogen is left by itself. There's the only element left. It's a part of Hofbrinkel, so we put a 2 after that. Now we got to reassess here. I didn't reassess that last time. I just realized both sodium and hydroxide, they both had a +1 charge, so they balanced out just fine. Zinc, however, has a +2 charge. Chlorine has a -1 charge. We need more chlorine here to balance that out, so that would be 2 chlorine would bond for every 1 zinc. that's it. That's all there is to it. It's an extra wrinkle here, just to figure out which element's gonna go where. It gets a little bit tough when you start adding things like polyatomic ions. So you like, where exactly does the ion start and end? I might do another video in the future on that, just how to differentiate between the two. But for now, this is the simplified how to predict products for single replacement chemical reactions. Anyways, hope you enjoyed the video. I hope it was helpful. If it was, leave a like, subscribe, and I'll see you guys all in the next one. Take care.